The Doppler effect in medicine. First I'm going to look at the Doppler effect in general with the simple example of this duck swimming across a pond. As he swims he produces these ripples, but as he's swimming to the left, the ripples in front of him bunch up. The ripples behind get spread out. As the duck swims, we get this sort of effect. If that has taken 1 second, an observer here will have seen 1, 2, 3, 4, 5 waves pass them, so they will see a frequency of 5 Hz. An observer here will have seen just 2 waves pass them, so they'll see a frequency of 2 Hz. We experience this effect with sound every day. As a car whizzes past you, it has a higher frequency coming towards you and a lower frequency going away. Something like this. Meow. Let's look at this situation in a bit more detail. Here we have the duck moving away from the observer with the speed v. We know that wave speed is equal to frequency times wavelength, and here I'm going to use the symbol c. This is normally used for light or electromagnetic radiation, but it just helps us to distinguish between c, the wave speed, and v, the speed of the object producing the waves, in this case the duck. In 1 second we'll have produced f waves. The frequency tells us the number of waves per second, and the source will have moved a distance v, as distance is equal to speed times time, and if the speed is v, we will move a distance given by the magnitude of the speed in 1 second. The waves will have moved in this direction with a speed c, and so they will have moved a distance given by the magnitude of the wave speed in 1 second. So the wavelength of the waves is the distance between them, given by the distance moved by the duck v, the distance moved by the waves c, divided by the number of waves produced, f. So the change in wavelength will be given by the wavelength caused here minus the wavelength of a stationary object. We can simplify that to show that the change in wavelength is given by the speed of the object over the frequency of the waves. We also know that frequency is equal to wave speed over wavelength, which we can substitute in here to get that the change in wavelength is equal to the object speed multiplied by the original wavelength over the wave speed. Or rearranging, we get that the change in wavelength over the original wavelength is equal to the speed of the source divided by the wave speed. We can also write that the change in frequency over the original frequency is equal to the object speed over the wave speed, but this only applies when the object speed is much less than the speed of the waves. This will be the case in A-level problems. We can experience the Doppler effect when waves are reflected. Here the waves are reflected off a stationary boundary, and the wavelength and frequency are not changed. However, in this case, the waves are approaching an object that is moving away from them, and now you see the wavelength is increased and the frequency reduced. If waves are reflected off an object moving towards them, the wavelength will be reduced and the frequency increased. The amount of the change in frequency allows the speed of the object relative to the source to be calculated. This can be used to find the speed of blood. Here we have an ultrasound transmitter and receiver sending ultrasonic waves towards the blood, which is moving away from the ultrasound. In this case, the wavelength of the waves reflected off the blood will be increased, the frequency will be reduced. This allows the speed of the blood flow to be calculated.